So radio waves. Where I left off last time, a week ago now, was talking about the structure of sort of the simplest of radio waves. And this is greatly simplified. It's real, but it's greatly simplified. The basic underpinnings of a radio wave and all of radio wave siblings, which include light, is that they have no electric charge associated with them. They are simply electric and magnetic fields endlessly recreating one another. And once you get one of these launched, which is the next story coming up, once you get it launched, it is self-perpetuating indefinitely. It can't stand still. It has to move because of the nature of the relationship between the electric and the magnetic fields. They both have to be changing with time, and that change in time carries with it the need to actually move. They move obviously very fast, the so-called speed of light. And what else about it? You have to have both fields, the electric and the magnetic field. You can't have just one, because the electric field and its change with time is responsible for making the magnetic field. And the magnetic field and its change with time is responsible for making the electric field. They're a team, and they head off very fast. One word about the speed of light. The speed of light, sort of in capital letters or something like that, is a specific speed in our universe. It's actually, calling it the speed of light understates its importance. Even if there were no such thing as light, that speed would be special in our universe for reasons having to do with the whole Einstein revolution of the early 20th century, the so-called relativity. So it is the special fastest speed, and light does travel at it for good reason, as long as there's nothing present through which the light's traveling. It's not traveling through anything, like air counts. Air is something. Light can travel through empty space, and then it travels at the speed of light. When you start putting stuff in space, like air or glass or plastic or water, light actually slows down a bit because it polarizes those materials. It pushes the charges around in those materials, and that causes the light, in effect, to linger. It gets tangled up with the materials that it's polarizing, and it slows down a bit, which is a story we'll come to. But for right now, we're just thinking, you can think in terms of empty space. Air slows it down a little bit because air is pretty light and fluffy, but it doesn't go entirely at the speed of light. It goes at a speed slightly slower than that. I will try to refer to it as the speed at which light travels when it's a non-interesting speed, like the speed at which light travels through water, because that's not the speed of light, okay? Not terribly important, but I'll do it anyway. Okay, so about this wave, as I've drawn it here, or as I've animated it in some of the animations on the figures from the textbook, or I've shown you on projected up here, we're looking at very simple waves, and we're looking at only a tiny piece of them, only the piece of the wave along a single line, which is a really small part of what might be a bigger wave in 3 dimensions, really. And to give you sort of an analogy to think about, think in terms of the waves on the surface of water. If you take the waves on the surface of water, which you've obviously seen in many, many different contexts, and you just simply pick out a line across the surface of the water and just watch the wave undulations along that line only, you've already simplified the wave a lot. You've taken out things like, sometimes waves are if we forget that line for a moment, we watch the whole wave, sometimes it's undulating like this and heading off to your right, and we're just watching one little slice through that wave. Or it could be ripples on a pond where you've dropped a rock here, and the ripples that are going out, they're not going sort of as straight surfaces that are, or well, as structures like a washboard. They're not doing that, but instead they're going out kind of as rings. You've watched the rings go out on the surface of water when you drop something in there. So the rings have a different shape than the washboard look that you get with waves that have been coming for a long distance and are sort of pass you by. The point of this being that if you just look along that one line, you're missing some of the details of what the wave really looks like in all of its glory, even on the surface of water where it's got sort of 2 dimensions to work with. You're taking one slice of what is actually a 2-dimensional structure. In this case, we're taking one slice along a line that's actually of a 3-dimensional structure. That line is not the only line we could choose. We could follow this line, or we can move a little away from you and follow a different line, or we can move up and follow yet another kind of line. So they all actually do matter. And I'm only following one line, which throws away all the details about what life is like to the left and right of the line, or above and below the line. That actually does matter. Fortunately, we can mostly not pay attention to it. We will see things like the radio wave that comes from an antenna. If the antenna is way over to our left, transmitting a wave, the wave that goes by is going to be a lot like the washboard structure, where its structure along this line and its structure along this line are almost indistinguishable. Nothing much changes. It's got its electric and magnetic fields here, and it's got its electric and magnetic fields here, and you can't tell the difference. Or if you go up, can't tell the difference. It's just the same structure, just slightly shifted over. If the transmitter antenna is right here, though, it's like the rock dropped in a pool, that kind of structure. So the wave, instead of going by as a washboard that's uniform for all practical purposes everywhere around, it's got a ring character to it. It's coming out from the antenna like the rings, like the ripples on a pond. And so if you follow the structure along this line, you'll see something. But if you go over here, it's going to look kind of weird, because if you're right in line with the antenna, things are simple. If you're cockeyed with the antenna, they're kind of messed up. So instead, you better to follow sort of the radial direction away from the antenna, as though it were spokes on a bicycle wheel. Then you'll see the same structure reappear. So from an antenna like this is an antenna. The wave that's going to come out of an antenna, it's going to love to travel along what's called a radial, in the radial direction, along a path that starts right at the center, in this case, the antenna. It's going to shoot straight away from the antenna. It'll give you a nice, simple, ripply structure. It'll look just like those things we've got drawn up there. If you go above and below dead center, it gets a little complicated too. If you go directly above the top of the antenna, there's actually no wave coming out of there. Can I explain why that? We'll see why that happens later on. But what I just want to convey to you at the moment is this is a very simple wave, and we're looking at a little piece of a potentially more complicated wave. We'll try to focus only on the waves that are pretty simple to start with and simple pieces of them, and just try to give you an idea of roughly what's going on. The details, there are people who spend their whole lives dealing with the shapes of these waves and the antennas that launch them or the antennas that collect them. This is the whole world of as well as part of, I suppose, electrical engineering and optical sciences, optical physics. There's lots to be done in these territories, and so you've got to take a little pieces that are good enough. Incidentally, one of the best sources of a very pure, simple wave, it's not the source of a radio wave, it's the source of a light wave, is a laser. The laser pointer, the wave that I'm sending across the room and that's hitting the screen over the wall over there or hitting the screen up here, that wave is really simple, which is what makes lasers so useful for studying the character of light and things associated with light. That wave is so simple, it's very much like one of these simple waves as compared to what? As compared to the light coming from a flashlight. The light from a flashlight actually consists of lots of little independent waves. And it's like buckshot. It's just lots of little waves, and each one of them is fairly simple, but you got a whole bunch of them at once. It's like throwing a handful of sand into the water and watching all the waves that come out of that. It's too complicated. So we'll try to stick with the simple waves. The simplest waves for light come from lasers, as we'll see later on. the simplest waves for radio come from radio antennas. You're very deliberately building a wave and sending it on its way. It has very simple structure. We can even simplify that further, and I'm going to do that. But even in it's more complex, it's richer complexity. It's not that complicated. The radio waves from radio antennas are pretty simple. All right? So having gone on at length about that. These two waves, again, we're looking along one line, throwing away, paying no attention, in effect, to the other lines above and below, left, right, above, whatever. And even then, there is some complexity along that one line. In this case, these waves are very pure in terms of wavelength and frequency. They are a single wavelength, single frequency. And what does that mean? Partly it's remind you what I said last time, and that is the wavelength of the wave is, you find that by taking the wave as it goes by this line that I'm waving my hands about in front here. So we're along this line, and we stop time momentarily. Just freeze frame, okay? And if you measure the distance from one feature on the wave to its like feature, one wave structure to the right or left, that distance, in this case I'll pick arbitrarily the peak of the electric field upward and the peak of the electric field upward, those two, distance from there to there, that's the wavelength of the wave. Just to give it a name, and you can count the number of wavelengths to get somewhere if you want. So that's wavelength. It's measured in units of distance, like meters, or feet if you like, but meters are more useful. Now, if we let time start again, okay, we're back, time is going. And now, if you watch the features go by from one location in space, so like watch the crests go by. In this case, by crest, I'm talking about the maximum upward electric field. Watch that crest go by. A little while later, this whole structure will move to the right, and a new crest will come in to take the previous crest's place, and you can watch them go by. 1, 2, 3, 4. That's what's known as the frequency. The number of crests you see go by, or number of features you see go by of the same feature per second. That's frequency. Is that okay? This applies to radio waves. It applies to sound. If I were to sing a note, which I won't bother doing, but okay, okay. Pick a, nah, I shouldn't even try. Yes. If you watch the crests go by of those different notes, you'll see, okay, if I pick a low one, that's somewhere in the 50 hertz, 100 hertz range going by. So the crests going by are very few per second. But if I go up here, it's higher note, and more crests going by per second, higher frequency. All right. I'll stop amusing you, or me. So you watch the crests go by, and that's frequency. And I told you last time that if you take the product of the frequency of the wave, that is how many crests go by per second, and multiply it by the distance between crests, that will give you how far a crest will travel per second, which is the speed at which the wave itself is traveling. And in empty space, that will be the famous speed of light. So if you take the spacing between these, let's suppose that is 3 meters between crests, and you watch them go sailing by, and you count them, you'll get to about 100 million in 1 second. So 100 million, often called, it's 100 million per second is the official unit, but often we'll put in the word cycle, because you're talking about the cycle of this rhythmic thing. So 100 million cycles per second, which has a shorthand name, it's called a hertz, after a physicist Hertz, H-E-R-T-Z. So 100 million hertz times 3 meters wavelength will give you 300 million meters per second. And that is how fast light travels, give or take a tiny bit. Okay? So, And actually, 100 million cycles per second is part of the FM band. So FM radio includes frequencies like that. And the wavelength of FM radio is about 3 meters in that vicinity. All right? I can't quite reach the full length. It's a little longer than my arm's reach, is the wavelength of an FM wave. If it was zipping by and we went to measure it, here's one crest, I'd have to walk a little bit over here. Here's another crest. Okay? Any questions about the structure of a radio wave? Wavelength, frequency, the speed at which the whole structure whizzes by? Okay, I also did tell you last time that if we reverse the magnetic field, it's always perpendicular to the electric field, and the two are both perpendicular to the direction in which the wave itself travels. If you reverse the magnetic field, so that instead of coming toward us, as in this drawing, it went away from us and created that same structure and then let time happen, the wave would travel to the left instead of to the right. So it's the relationship between the electric and magnetic fields that determine which way the wave actually travels. All right, so having done all that, that's the wave. Once you get it started, it goes. How do you get it started? And the answer to that question is, I'm going to ask this question here first. If you place a positive test charge in the radio wave, and there's nothing else around at all, just completely otherwise empty space, will the test particle experience a force? You okay with the question? How many think yes? How many think no? Okay, a few people going for no, but most of you are going for yes. And the answer is indeed yes. That radio wave has a real electric field. It's truly there. The fact that there are no charges otherwise around except for this test charge you're using to sort of explore the radio wave doesn't matter. You can have electric fields without charge around. In this case, the electric field is created by the magnetic field, and the magnetic field is by the electric field. But they push on stuff. The magnetic field will push on magnetic poles if you've got them there, just as the electric field in the radio wave will push on charge. And that's going to give you an idea of how the radio wave is received. When a radio wave comes whizzing along through empty space and encounters things that have electric charge in them, like a piece of metal, the electric charges will get pushed. They'll start moving. And actually, if it's a nice, clean, smooth sheet of metal, the electric charges will move in a remarkable way. They will perfectly take in the wave that hit them. So this is getting ahead of us a little bit. They'll take the wave in, and they'll move up and down, and they will actually launch their own wave. Once they're moving, we'll see in a second, moving charges, particularly accelerating charges, launch radio waves. So the radio wave will come in, get the charges going, woo, up and down, and they will launch a radio wave, and they will reflect the wave that came in. When the dust settles, the radio wave that was whizzing along, say to your right, that encountered the sheet of metal, will not continue beyond. It's gone. Where'd it go? It will reflect off the sheet of metal and go back approximately from whence it came, depending on how you've angled the metal. This is how a mirror works. You don't think a mirror is working with radio, but they do. But they certainly work with light. You know, why does light reflect off of a metal mirror? And I'll be picky about it, call it a metal mirror. There are other mirrors. And in that case, the reflection comes about because the radio wave does have, the light wave, does have electric fields in it. It pushes charge around. The charge bounces in such a way that it takes in the wave that got this all started and sends out a new one as a reflection. So there's the basic idea behind most of the mirrors you encounter. It all has to do with moving charges caused by electric fields. So this is sort of introductory to the whole idea of how you get an electromagnetic wave launched for the first time, and you do that with accelerating charge. It is possible to do it with accelerating magnetic pole too, but that's so rare. It's not worth paying much attention to at the moment. The point is this, that if you have stationary electric charge, it's purely electric. Static charge, that's where we started this part of the semester. was with static electric charge just sitting there on, I don't know, a candy wrapper or you after you've walked across the carpet. That charge creates an electric field, but nothing else. There's no magnetic field associated with it. However, if you have electric charge that's moving at a steady rate, say through a wire, now you have also a magnetic field, because moving charge is magnetic, right? Current. But that magnetic field is constant. The charge is constant. Nothing's really happening interesting as time goes by. The current keeps flowing, the magnetic field keeps being there, and the charge keeps moving. So far still, no electromagnetic wave. Where do you get the electromagnetic wave? Make the charge accelerate. This is the first real change with time. So instead of putting the current through the wire and keep it continuous, send the current through the wire and then slow it down, and then send it back the other way and slow it down, back and forth. Have the current slosh back and forth like water in a tank. Have the current slosh back and forth through the wire. In that case, the charge is moving around. Sometimes you got more charge here, sometimes you got more charge there. The charge is changing with time, and that creates an electric field that changes with time. You could see if somebody's moving charge up and down a wire, like this wire. If you take this wire and shove positive charge on the bottom and negative charge on the top, and then moments later you have them swap places, and you have positive on the top and negative on the bottom, back and forth, that's pretty easy to notice. If you were an electric charge sitting over here, you go, whoa, I'm being pushed up, down, up. It's an action that affects nearby electric charges. The other thing is, because the charge is sloshing back and forth, the magnetic field associated with the charge moving, remember, moving charge is magnetic. In this case, yes, the moving charge is magnetic, but the moving charge is going back and forth. So the magnetic field that charge produces as it moves is changing up and down, back and forth also. The long and short of it is, when you've got electric charge that is accelerating, and even if whether it's on an antenna or it's just somebody shaking it up and down, or thousands and millions of different contexts, it creates an electric field that changes with time because the charge is not always located in the same place. It creates a magnetic field that changes with time because the charge is moving in an uneven way. And those two, a time-changing electric field, a time-changing magnetic field, they can create each other, right? Changing magnetic fields are electric and changing electric fields are magnetic. They have an opportunity to create one of these structures that travels, the waves that travel, the electromagnetic waves. So that's the way you launch one of these waves. The most important way in which to launch these waves is accelerating electric charge. And where does this show up? It's going to certainly show up in all the radio transmitters you ever encounter. So all of them are going to have electric charge that's going to be forced to accelerate using fairly familiar techniques to push on it and shove the charge up, shove the charge down, back and forth. Where else it shows up is that if you just get the charges that are in everything, we're all full of charges. Every surface, every object you ever encounter has charges in it. If you get those charges to jiggle about and accelerate first to the right, to the left, up, down, shake them around, which you can do with thermal energy, they will launch their own little radio waves. And because of the situation, the radio waves will have very short wavelengths, very long, very high frequencies. They will be in the range of electromagnetic waves we call light, or more notably, infrared light. All the charges in you and everything around us right now, they're all jiggling around with thermal energy. They are therefore accelerating. They are therefore launching their own little waves. Those waves are in the infrared light. They are the thermal radiation that comes off of things. So if you've ever seen thermal imaging of people or of surfaces and stuff, there are machines that can observe thermal radiation of room temperature type stuff, human temperature type stuff. They're seeing the little waves that are launched by the jiggling charges. Questions about that idea? Sunlight is the same thing. It's just that the sun is so hot. Its photosphere surface from which the light comes is so hot, the jiggling is so much more aggressive that the waves that come off of it are in the visible light by and large. You are seeing their thermal radiation. You're seeing all the little charged particles on the surface of the sun jiggling around, launching little waves. Out they go. All right? That's harangue about the launching process. You launch the waves with accelerating charge. So how do you actually get that going in a radio transmitter? For objects that are simply jiggling around with thermal energy, you know, that's another story. Let's launch a wave very deliberately, not with the randomness of thermal energy, but with the deliberate interest in launching this very specific wave with a specific wavelength and therefore a specific frequency. How do you do that? And the way you do that is by shoving charge, say, up and down in a vertical antenna or left and right across a horizontal antenna, somewhere. Just get a venue in which to take a lot of charge and slosh it back and forth some way or other. And to do that, I want to introduce a device in which charge sloshes nicely. And just as an analogy, you know, sloshing charge is hard to see, but sloshing water, not so much. You can see water slosh. So surely at some point you have sloshed water back and forth in a pot or in an aquarium or in the bathtub, and you can get the stuff going back and forth, literally sloshing, and it piles up on one side, piles up on the other, back and forth. Interesting features of that is that you can get it going and it has a natural rhythm to it. The rhythm is driven by the forces that push on the material when it's away from an equilibrium. There's some equilibrium. In a tank of water, equilibrium is dead flat. The water wants to all be at the same height. This is where water settles down naturally, having gotten rid of as much total potential energy as it possibly can. If you get it sloshing, you've taken it away from equilibrium, an act which requires investing energy into it, and it then sloshes back and forth about the equilibrium, typically with a natural rhythm. And the natural rhythm is determined by some issue of the forces pushing it back towards equilibrium and the inertial character of the stuff, like how much it wants to keep doing what it was doing. So if the forces that push it back towards center are weak compared to its own inertia, it's going to just keep doing what it's doing for a long time before you get it finally come back. It's going to be a very slow slosh. On the other hand, if the forces pushing it back towards equilibrium are quite strong compared to its inertia, they're going to turn around the slosh very quickly, and it's going to be fast. So you can play with the characteristics of water in a tank and get it to slosh quickly or slosh slowly. Typically, the bigger the tank is, the more mass it has, the more inertia it has, the harder it is to get it to come back. And so it's a slower slosh. The slosh in a cup is the slosh in a bathtub more, okay? All right, so that's the world of sloshing of real water in real tanks. How about sloshing of, well, for pretend water? Charge in what's called a tank circuit. So drawings up here are what are known as a tank circuit. There are 5 drawings here, and I'll show you an animation in a minute of a tank circuit. A tank circuit consists of only 2 electrical devices. One of them is an electromagnet, just a coil of wire, nothing else, typically no iron in it, just a coil of wire. And for this context, it's given a new name, and instead of calling it an electromagnet, it's called an inductor. And its behavior is that when you run current through it, it develops a magnetic field. And as the magnetic field is building up, the current has energy taken out of it to pay for building the magnetic field in that coil of wire. And so it's hard, it takes some doing to get the current to build that magnetic field. Basically, the inductor fights the rising current. It slows that current down because it actually pushes the current opposite its own flow, direction of flow by way of an electric field. As the magnetic field is building up, it creates an electric field. And that electric field does negative work on the current and sucks energy out of it. So it fights the rise in the current by pushing the current backwards during the buildup. If you try to turn off the current, it also fights. When you try to turn off the current in an inductor, the magnetic field, as it begins to get smaller, produces an electric field. And what does the electric field do? It keeps pushing, it pushes the charges in the current forward. Come on, guys, keep going, keep going. The inductor has this interesting characteristic then. It always fights changes in current. It doesn't like them. It opposes a rise in current at the beginning, and it opposes a decrease in current at the end. It wants to keep the current steady. The other feature about it that's in this case very important is the inductor stores energy in its magnetic field. So when you really get current, when you finally get a lot of current flowing through the inductor, it's got lots of energy in it, in the magnetic field associated with that current. Because as I've told you many times, magnetic fields actually have energy in them. That's the inductor. Questions about the inductor? The details, they may not sink in at this point, but the main thing is it loves when it stores energy in its magnetic field. That's the most important part of my current story. The other component is what's known as a capacitor, and we've seen these guys too. A capacitor is just two surfaces with opposite charges on them, separated by a gap, insulator, whatever you like. Two surfaces, and you can put positive charge on one, negative charge on the other. It has no net charge, but it's got separated charge, and that stores energy. It stores energy. You can either think of it as owned by the charges, which would love to get together and release that extra energy, or you can think of it as energy stored in the electric field between the charges. And that's the way we'll think about it right now, is that electric field that's between the two surfaces gets stronger and stronger as the amount of separated charge accumulates. More positive, more negative, bigger field. And the energy in it then increases with the amount of charge that's stored. So the most important feature for the moment of a capacitor is that it stores energy in its electric field. It has the behavior, I told you that the inductor has the behavior that it fights changes in current. A capacitor has the behavior that it fights changes in voltage. The two surfaces have different voltage according to how much charge they have on them. The one that's positively charged naturally has a higher voltage than the one that's negatively charged. And if you try to change the voltage between them, that's tough because you're going to have to change the amount of charges on those two surfaces to change their relative voltage. You can't just say, okay, I'm going to make you twice the voltage. No, you have to put on twice as much charge on it. So the capacitor fights changes in voltage. The inductor fights changes in current. They are very important building blocks for electronic devices. But in this case, they're building one of the world's simplest electronic devices, the tank circuit. You just tie them together. And when you just tack them together like that, you have a weird circuit. It's a weird circuit in that there is no complete loop around it. Now, I've told you all along the circuits always have a complete loop. Well, not always. This circuit actually has an insulating gap between the two plates of the capacitor. But otherwise, it's a complete loop. It's got a complicated complete loop, but otherwise it's complete. And that gap turns out not to be very important. It still has a lot of characteristics of an ordinary circuit. So let's take this crazy circuit and let's start at one moment in time, freeze frame, and let's pile positive charges on the top surface of the capacitor. So this capacitor is just two sheets of metal staring at each other across empty space. And we'll put positive charge on the top one, negative charge on the bottom, and because time is frozen, nothing happens. But there is an electric field between those two plates, in this case pointing downward because the positive charge is on the top. And there's energy stored in that capacitor. I showed you, incidentally, a capacitor early on in the semester, that big blue cylinder that I charged up with batteries, and then we short-circuited it with a screwdriver. All the energy came out. So this is typically a littler guy. So there it is. Now let's let time happen. When time happens, these charges would love to get together, positive, negative, ooh, that would be so great. And they have a route. They can go through the inductor to get together. So they do. So they begin to flow through the inductor. And as they do, the current in the inductor begins to increase. And I told you, it fights changes in current. It does not like a rapid change in current. It slows the current rise down as it builds its magnetic field. So as the current goes through this thing, the magnetic field begins to build up until finally there will be a moment when the capacitor has run out of a stored charge, no separated charge left, and therefore no energy in the capacitor, but all the energy is still there. It's in the magnetic field of the inductor. Now the magnetic field of the inductor begins to collapse as the current starts to diminish. And as it diminishes, that decreasing magnetic field creates an electric field that recharges the capacitor. It recharges the capacitor upside down, positive on the bottom. So let me go over to the animation of this guy, and I will hope it's followable. It's also in the... Yeah, it's recycling automatically. So here's... I'm sorry I flipped it left to right. But there will be a moment when all the energy is stored in the capacitor. There it is. Positive is on top, negative on bottom. And there'll be a moment when all the energy is stored in the inductor. And then there it is. Now here's all the energy in the capacitor. Now here's all the energy in the inductor. And back and forth. And the charge is sloshing. It's sloshing back and forth between the capacitor's top plate through the inductor to the capacitor's bottom plate. And back. And the fact that the slosh works has to do with the magnetic fields, the electric fields. They all work together to shove the charge back and forth. No energy is disappearing. This assumes perfect conductors and stuff, which is not quite realistic, but that's okay. The charges really are going back and forth, and the energy is shifting between these two devices back and forth rhythmically. Questions about this idea? I mean, the details, you stare at it a couple times and get some idea of this. The main thing that matters, the thing that matters most is there is definitely accelerating electric charge in this. And there is a rhythm that's determined by characteristics of the capacitor and the inductor. How much they fight changes in voltage and fight changes in current, and they negotiate to create a rhythm that's determined by those. And you can engineer it to have the rhythm you want. All right? So where does that take us in going to launching a radio wave? Well, that structure can give us a nice rhythm with which to pick a radio channel. The radio channels, the channels of AM radio, by long history and convention, fall between about 550,000 cycles per second and 1,600,000 cycles per second, 1.6 million cycles per second. If you look at the radio dial, it goes from 550 to 1,600 on the AM, if you listen to AM radio anymore. There's a factor of 1,000 that's hidden from view, but it's there. So if you watch the radio wave coming by from, well, I'll pick a channel in Charlottesville, WINA is 1070. If you watch the radio wave coming from WINA, you watch the crest go by, 1, 2, 3, 4, 5. You count for a second, you'll count 1.070 million cycles go by. Is that okay? The wavelength will be just under 300 meters, very long. From here to 300 meters will take you across the Emmett Street, somewhere over into Brown. It's a long distance. So that's the wave. How do they launch that guy? Well, they launch it. They use a tank. First off, they almost surely have tank circuits around there that give them that rhythm. The tank circuit is designed to have a rhythm of 1.07 million cycles per second, the sloshing time. It does that. And they connect that to an antenna, and I'll show you what the antenna could look like, but this isn't quite right yet. The antenna is a piece of wire. And, you know, the piece of wire, it turns out, also has a natural rhythm. A piece of wire, if you just look at this piece of wire, there are moments when the bottom of the wire is all positive charge, and there are moments when the top of the wire is all positive charge, and the other end, of course, is negative charge. So this is having the weird behavior of it's got a separated charge accumulating on the two ends. Here's positive on the top, negative on the bottom, and here is positive on the bottom, negative on the top. We've seen that behavior before. Oh, and in between, of course, there's a lot of movement and there's a magnetic field. We've seen that behavior before. We saw that with the tank circuit. The tank circuit had this arrangement where the capacitor had a positive, had the two surfaces of the capacitor one developed positive charge, one developed negative, and then they swapped. And then back and forth by way of the inductor. The charge moved through the inductor to make this happen. In this case, we've got the tips of the wire are having that same behavior. They're going from, they're developing separated charge, and then it's swapping by way of the middle of the wire and then piling up. The point of all this is a tank circuit again. It just doesn't look like one. It's a tank circuit. I can pull the tank circuit back out. Where's tank circuit? There it is. Here's tank circuit. Let's grab that plate right there and this plate right here, and we'll shrink them, which physicists do this all the time. You just sort of deform something continuously, and you just pretend it's the same, like nothing changed. Like I can take your gold clock and reduce it to a little ball and say it hasn't changed. I mean, all the values go on it. I'll stop. Okay, so the point is, let's shrink these plates to just very, very little, and let's take the top and bottom plates and just yank them apart and unwind this coil. When you do that, if you imagine just deforming this tank circuit and stretching it out straight, you end up the wire. You end up with the antenna. Questions about that or observations about that? Does that make sense? Yeah, Jesse?
On a capacitor, why don't the opposite charges attract? Why do they move between them?
So Jesse's question is, why do these opposite charges attract? Why do they move between the surfaces? Why don't they just jump, I guess, in effect? They can't jump because they're forbidden from moving in that area. There's no conductor between them. There's no path for them to go. They are attracted, but for chemical reasons, they can't leave the metal. They're forbidden to leave, like they're on a railroad track. But what they can do is they can flow through the wire, and they are actually pushed by an electric field. There is an electric field in the wire that pushes them. So they take the second best opportunity, which is instead of going directly across empty space, which is forbidden for chemical reasons or materials reasons, they go through the wire to get together, and it works just as well. Is that okay? So if you take this tank circuit and just yank, oops, overshot, and just yank it straight, that's still a tank circuit. It has a capacitor. What's the capacitor now? It's the tips. This surface here and this surface here, they're far apart now. That's true, but they can still store energy in their electric field. And the coil's down to just one straight wire. It's not much of a coil, but it still has a magnetic field, and it can store energy in it. So the electric field here, it's still storing energy, alternately with a magnetic field, which is still storing energy. It's just a weird tank circuit, and it's got a natural rhythm. And if you want to have the natural rhythm of this tank circuit match the natural rhythm of the other tank circuit, you have to choose the length of the wire right. And this is what's known as a half-wave antenna, meaning that it has its natural rhythm will spontaneously launch a radio wave that has a wavelength that's twice as long as it is. So if you want to launch the WINA radio wave, which I said was about a little less than 300 meters, you want this guy to be a little less than 150 meters long. It will naturally have that sloshing rhythm that it needs to launch a 1.07 million cycle per second wave. Is that okay with people? I'm obviously not going to finish everything. But if you look here and notice that the electric field is changing with time, of course. The magnetic field is changing with time. They are at right angles to each other. The magnetic field is this loop around the coil, around the piece of wire, but it is changing with time. Those two, they're at right angles. They're a lot like a radio wave. And sure enough, they launch to some extent. Not all the energy goes into the radio wave, but some of it does indeed go out as a radio wave. So I could if we follow the magnetic field here, the electric field, you follow those out for a while, there will be a radio wave coming out of here. It'll be heading to the right on the right side of the structure. It'll be heading to the left on the left side of the structure. So this is one of these cases where the three-dimensional pattern is interesting. It involves radial waves that head out from that antenna. They also do not head off the tip of the antenna. There's no wave heading vertically upward, which is fine because most listeners are not vertically above WINA's antenna. They'd get bad reception. Okay, WINA doesn't use this full antenna. They use half of it, and I'll talk about what's called a quarter wave antenna on Wednesday.